All right. We join this broadcast already in progress. Switch to decaf. Fy 20y minus 2 lambda y 0. And of course, f lambda, capital F of lambda, is minus well, where does that leave us? This fx equals 0. That factors into what? 2x 4 minus lambda equals 0. That gives you x equals 0 or lambda equals 4. We haven't had that come up before. Yeah. Well, Fy, from Fy, we get, after a 10 off and a y off, you get 2 minus lambda equals 0, y equals 0, lambda equal 2. Question. Did I just find the origin again? 0, 0? No, I did not. The reason is I found places on the perimeter. So down here, these lambda x equals 0 corresponds to where? It corresponds to this point or that point back there, right? That's where x equals 0. It's on that perimeter. It's on the constraint is what I'm talking about. Similarly, when y equals 0, I'm talking about here or back there. Right? Those are places y equals 0. Now the lambda equals 2 gives us. Well, okay, so we have here just hang on to that a second. You don't do much with it. If x equals 0, x equal 0. Well, I have x squared plus y squared equal 4. If x equals 0, that implies that y squared equals 4, which implies that y equals plus or minus 2. So that gives us the points 0, 2, 0, minus 2. Duh! 0, 2, 0, minus 2. Those are those 2 points there. You see how this stuff kind of starts to validate? And when we do the other one, y equals 0, x squared plus y squared equal 4 implies x squared equal 4 implies x equal plus or minus 2. So that gives what? 2, 0, minus 2, 0. So now we're talking about on the perimeter of the disk, right? So those are places we could have maxima and minima. Now, next thing, it's time for one of our charts. So here we're going to have points. We're going to have over here critical points, CPs. Those are just 0, 0. And we're going to evaluate 4x squared plus 10y squared at 0, 0. That, of course, gives you 0. And then we're going to have these other points. 0, 2, 0, minus 2. 2, 0, minus 2, 0. So this is like evaluating the edges and corners, except we don't have corners. So this is going to give us what? If we put 0, 2 into 4x squared plus 10y squared, this is going to give us 4 times 0 squared plus 10 times 2 squared equals 40. 0 minus 2, 4 times 0 squared plus 10 times minus 2 squared, also 40. Next, 4 times 2 squared plus 10 times 0 squared, 16. 4 times minus 2 squared plus 10 times 0 squared equals 16. Okay. Ergo what? What is the max and minimum? Ergo. F of x y has a minimum of 0 at 0, 0. Just like we expected with our eyeball test at the beginning. F of xy has a maximum of 40 at those 2 points, 0, 2, and 0, minus 2. All right. Not so bad. Just check the 15.
Not so bad, he says.
That one, this one isn't so bad. I should never, I'm such a bad teacher should never say it's easy. Of course, I have a button in my room.
That was easy.
You're only supposed to hit the button after everyone thinks it's easy. Like when people are, how's this going to work out? And it comes out, oh, I can do that. That's when you hit the that's easy button. Of course, I hit it all kinds of lot of times. What do I care about student self-esteem? All right. Yeah. No snowflakes here, right? So, okay. Let's go to chapter 14. Oh, wonderful. I was looking at it in my office. All right. Let me see here. Chapter 14 is, okay, chapter 13 was the multivariable version of chapters 2 and 3 in our class, which means nothing to them because she took Calc 1 elsewhere. Which needs to be heard. Really, can you get it better than, you know. No, but no, chapter 2 was derivatives, chapter 3 was application of derivatives. So chapter 13 was the multivariable version of those two. This is going to be multivariable version of chapter 4, 5, 7, 8. All of those were learning how to integrate, what an antiderivative is, learning integration techniques, such as trig substitution, parts, and all that stuff. Right?
I remember chapter 7. That was rough.
Yeah.
That was rough.
Chapter 8. Chapter 7 actually was applications. But no, chapter 7 is not a crowd favorite either. Chapter 7 is applications of the integral. That's like work problems. How much work to pump oil from one tank to another on a prime number Thursday in October.
8 was the one with all
It
the
is.
schools. That was the one that we took. That was the first test we took in quarantine. Back home.
Oh, is that right? That's right.
Yeah.
Holy smokes.
Remember it very vividly.
Well, that honestly is torture. That is cruel and unusual punishment to learn that one online. I pretty much do not believe in online calculus, but there's a lot of places now. Online calc, online college algebra, right? And lots of people here are going, oh, I'd rather have it easier. They know that it's going to be a little bit easier if it's online, because they know they can maybe look at some other resources during the test and things like that. And they can also, teachers aren't going to put quite the rigor. You can't put quite the rigor online that you have in a classroom. But my issue is, look, our students go on to be engineers, doctors. I don't want them. I don't want a guy building my bridge who took the easiest calc class he could get, right? Besides that, I had my own kids in here. And they went on to other schools where they had to pick up, where, like they took Calc 1 and 2 here, and they had to go to the schools where Calc 3 picked up, where Calc 3 is supposed to pick up. And my son was in a Calc 3 class out at UNO. By the way, they test everyone coming in. They don't care what your grades are. They don't care what your ECT scores. You take our tests. You take our tests, and based on that test, you go in the course we tell you. We don't care if you had it somewhere else. You didn't learn it, so you're taking it again here. That's what we want to do. There's too many are getting these, honestly, wimpy versions of classes online or sometimes in dual credit situations.
Or they just forget.
That's allowable too. To forget, that's allowable as well. But it comes back a lot better if you once knew it than if you took some marshmallow somewhere, and there are plenty of them out there. Multiple integration. Okay. What do you do? What would you do if you saw this? I want my mommy.
I would just integrate it twice, even though that's.
Yeah, it looks like you got to integrate twice, doesn't it? Right? And it kind of, doesn't it look like maybe it should go this way? Bracket there, bracket there. And we do this integral, and then we do the outside. Now, instead of partial differentiation, we're going to do partial integration. I know you can't wait. Don't worry. Smart aleck sarcasm is a gift bag. But what you do when you differentiate partially, you leave all other variables as constants. You treat them as constants. Because in fact, they do not change along those planes parallel to the coordinate axis. So now we're going to integrate partially with respect to y. So y, and then we have this x squared. X squared is just a number. Pretend like x squared is 4. Because when you're integrating with respect to y, x isn't changing. Just like when you're differentiating that with respect to y, x is held constant. You treat it as a constant. Ergo, this would wind up being y. You'd have an integral on the outside. X squared is a number. If that were 4, and we were integrating 4 with respect to y, it'd be 4y. We're integrating x squared with respect to y, so it's x squared y. X squared is a constant, like a number. And then we're integrating y with respect to y, and that's going to be y squared over 2. Right? Right? Then that gets integrated with respect to x. Now, with respect to x, we treat all the y's as constants. So this first term, x squared y, we treat y as if it were a number 5. We integrate the x squared part, which is x cubed over 3. So this is going to be x cubed over 3y plus, we're integrating y squared over 2 with respect to x. So y squared over 2 is a constant. So it's going to be y squared over 2x. And since it's an indefinite integral, plus c. Right? Okay, so that's the idea. This is partial integration, this chapter. Partial integration. All right? Let's move on. Iterated integrals and areas of the plane. These big words, right? I almost feel like skipping this. Okay. The reason why, this is one of those theorems that I know why they put it in the book, because somewhere you got to state it, right? But I don't think many students looking at this are going to go, okay, I see what this is going on. Yeah, I don't think many of us do that, right? This is better looked at after actually doing a problem. So that's what I'm going to do. But I did show it to you as due diligence, right? We're going to need that too after. Okay. Now let's get back to some stuff you know how to do. We're going to do this Calc 1 way, Calc 3 way, and an encore Calc 3 way. All right? Okay. The Calc 1 way was what? You're going to find the area between these two curves. First of all, what area are we talking about? It always helps to graph your area you're integrating. All right? So, pop quiz, 4 minus x squared, what does it look like? Well, if it were minus x squared, it'd be a parabola opening downward at the origin. If you add 4 to it, that moves that whole parabola up. So that goes
That was easy.
now minus x plus 4. We're going to have a slope of minus 1, y-intercept of 4. So that is going to look like what? It's going to go through this 4, same point here, and it's going to intersect over here at 4, right? So it's going to be so that's this, and this is this. So the area which oh, it's too tiny. This area here, I made it too tiny. It's going to make it a little harder, but we're up for it, right? We're up for it. Now, there's a Calc 1 way of doing this. It was you subtract the two. So the Calc 1 way was area equals integral. We'll figure out the bounds in a second. And since the parabola is on top, this is going to be 4 minus x squared minus the line on the bottom dx. Okay? We need our bounds of integration. We're integrating with respect to x, so we need the x coordinate here, 0. We need the x coordinate there. What is that x coordinate? Well, I'm going to delete some of that. How do we figure out what the x coordinate is there? We set 4x squared equal, 4x squared, oh dear, 4 minus x squared equal to minus x plus 4. Then, sound effects optional. Unless you're a guy. We're that way. That's what you guys are. And so this is the same as x squared. So I'll put that on the other side. X squared minus x equals 0. Do I like that? Yeah, I think I like that. So that's going to give me that x equals 0 or x equal 1. So this is the point 1, 3. So our x goes from 0 to 1. Okay? Let's do some stuff here. 4 minus 4. And so this is going to be integral 0 to 1 positive x minus x squared dx. That's going to be x squared over 2 minus x cubed over 3 from 0 to 1. We're just starting integrals in Calc 1. So this whole 0 to 1 and fundamental theorem. That's going to be plug 1 in, 1/2 minus a third. Plug 0 in, you get 0. So that equals 1/6. All right, that's Calc 1. Now, we're going to take a simple step up and do this the Calc 2 way. You might say, why do I have to do it the Calc 2 way if I can do the Calc 1 way? Because the Calc 2 way is going to get more sophisticated. So the Calc 2 way here is going to be, it's going to be like this. Oh, by the way, in Calc 1, you remember that, I'm going to erase this, but you remember if I integrate 1 dx from a to b, that was just b minus a. Because that would integrate to x, a to b, and that's b minus a, right? So the integral of 1 was the width of the integral. Linear width, linear measure. In Calc 2, it's going to be area. Oh, sorry, Calc 3. Area. Right? But that's what we're supposed to do, is find the area. So it's going to involve integrating 1. That's the punchline. It's going to involve integrating 1. So the Calc 3-way is A equals a double integral of, this is the point, so I'm going to make it bold, 1. And the way the book does this, the integral of a region R dA. And if you look back up here, the stuff we missed, oh, they didn't do it. So we're going to integrate 1 over some region with respect to this for area. Now, let me show you how that works. Here's the trick. And this is those slides that we missed. We're going to go up here and we're going to identify what does go from here to there. That's it. We're integrating in between there. And then we're going to let this little bar, little segment, slide between here and there. And as it slides, it adds up the area. I know what you think. This is getting to be voodoo, right? Add up the area, yeah. That's what happens. Here's the key. So we're going to have integral 1. Which direction is this? Which variable is changing along that red line? Y. X is fixed along the red line. So we're going to do the way I'm setting it up here, dy. And y goes from what to what? Well, what's y down at the bottom? Y equals 4 minus x. What's y up at the top? Y equals 4 minus x squared. I wrote it 4 minus x instead of minus x plus 4. You get it, right? So that goes here. The bottom, 4 minus x. The top, 4 minus x squared. And what that's going to do is as I move my line segment throughout that region, it's going to adjust those endpoints. Narrower together, farther, and then narrower together again. Right? Because those endpoints are narrow here. In fact, they touch there. They open up, and they get narrow again. And so these variables are going to adjust the length of that segment according to those two curves. How far do I want that segment to go? Now, since I want all of the area in there, I want it to go from 0 to 1. When I say it, what's it? X is fixed along that segment. So now I'm going to let x vary. I've already taken care of the y part. I'm going to let x vary from 0 to 1. Now, if I only wanted half that segment, I could do 0 to half. And it would only add up like to the halfway point, right? By the way, if I went from 0 to 2, out here, what happens? Well, out here, the parabola becomes the lower one. The line becomes the higher one. But I'm doing high minus low, so this is going to be negative area out here. And it will offset that area. Anyway, we'll leave that for a little bit. 0 to 1. This is what I want you to understand. Why? Where do we want that little bar to go from? From here to here, which is 1. Now I know that scale's not good, right? But if I'd have made it good, that would be even a smaller area up there. So anyway, not to scale. Right? All right, so what happens? 0 to 1. So I want that little segment to go, as it goes from 0 to 1, it adds up the area. And these make the endpoints, they determine, excuse me, the length of that segment. Now watch what happens. You can see that 5 times. Something cool happens here. Let's do the first integral. Oh, dx. Now just keep in mind, as a reminder, this is y equals that to y equals that, because we're doing dy. The outside integral is x equal that to x equal that. Now these are understood, being on the inner integral or the outer integral. But when we're getting used to this notation, keep those in mind, especially as you're setting stuff up. So what happens? If I integrate 1 with respect to y, what do I get? I get integral 0 to 1. I integrate 1 with respect to y, I get y. And that goes from 4 minus x to 4 minus x squared dx. So using the fundamental theorem, what does that look like? I plug in the top and subtract what I get when I plug in the bottom. So this is going to be integral 0 to 1. Plug in the top, 4 minus x squared. Minus what I get when I plug in the bottom, 4 minus x. Plug in the top, plug in the bottom, subtract. Does that look familiar? What we have left now is exactly that. So that's why I started with my comment, well, why do I need to do the calc 3 way when the calc 1 way works perfectly well? Because we're gonna soup this one up a little bit. This is gonna get turbocharged. And so we saw from before that equaled 1/6. Right? We don't have to crunch that one again because we crunched it up there. Right? Oh dear. Whoa. That's not good. Save this stuff, okay? Now, we have another encore. That's not all, folks. We have another way of doing calc 3. And this is an important skill that you must learn. All right. In fact, I'm just going to what's our area look like again? Oh, no, that's not what it looks like. That's what it looks like, right? Then we have the green coming down like that. And this was the point. That was the point 0, 4. And this is the point 1, 3. Notice this way we did this little red bar up and down. We did it in the y direction first. Why couldn't we do it in the x direction first? We could. So that's the other way I want to show you. What? You love it. Okay. Why not do it this direction? So our area, integral. We did dy first last time. This time we're going to do dx. And we're still going to do then dy. And it's still going to be of 1. So it's still the calc 3 way. Now there's going to be times that it will be easier to do it with y or with respect to x first. So this is a skill you got to be thinking of. Right. We're starting to learn to think in terms of, right? So I asked myself, on the outside, on the farthest end of that little red segment, what does x equal over here? And what does x equal over here? Well, this is the line y equal 4 minus x, right? When in doubt, coffee. That's 4 minus x. Okay. Well, what does x equal? X equals y minus 4. Right. So over here, it's y minus 4. Well, on the parabola, I have what? I have y equal 4 minus x squared. So x squared equals 4 minus y. X therefore equals plus or minus square root of 4 minus y. I don't like it. Well, the negative one would be over here. So associated with any point y, there's going to be 2 x's. One over here on that part of the parabola, one over here. I'm interested in the positive. So over here, this one is square root 4 minus y. So notice the endpoints of my little segment become my bounds of integration. So what's my lower one? My lower one is the one closest to the axis. It's this line again. That happened to be the line in both directions. That isn't always the case. So this is going to be the 4, y minus 4. And the top one is square root 4 minus y. Right? Now, that little segment is going to run. So I did dx first. That segment runs in the x direction. Now I'm going to let that segment go from my bottom to the top of my region. The bottom of our, now these are y's now, okay? Y down at this part is 3. Y up there is 4. So I have 3, 4. And we claim this equals 1/6. Okie dokie. Let's roll. 3 to 4. This is going to be dx, x evaluated from y minus 4, square root 4 minus y, dy. Most of the time, setting up the integrals most of the work. Not always, but most of the time, setting up the integrals is the work. So this is going to be integral 3 to 4. Plug in x, square root 4 minus y. Minus what I get when I plug in y, y minus 4. Oops. By the way, when you're done, you better not have any x's left. because you plugged in for the x's. You shouldn't have any x's left here because your result's going to be a number. Because now you're going to integrate with respect to y. So after you integrate with respect to one variable and you're done plugging in the bounds, that variable should be gonzo. Right? Hasta la pasta. Question. What's the antiderivative of 4 minus y? Oh, no. If it was y minus 4, it'd be easy. If it was y minus 4, what would it be? Y to the 3 halves divided by 3 halves. Excuse me. Y minus 4, it would be to the 3 halves divided by 3 halves. Well, I need the derivative of the inside on the outside. That's a negative sign. So this is going to be, antiderivative is going to be negative 4 minus y to the 3 halves divided by 3 halves. Yeah. Minus, the y is got the minus, so it's going to be y squared over 2. The 4 is a plus 4y, all integrated from 3 to 4. Yuck. Now I'm going to do something else first. I'm going to rewrite this 3 halves and put 2/3 up front. So that's going to be minus 2/3. 4 minus y to the 3 halves minus y squared over 2 plus 4y 3 to 4. It's going to be a long road to 1/6, right? So left, now we're going to need a bracket. Left parenthesis, plug in a 4. 4. That's going to be a 0. When we plug in a 4, that's a 0. Hallelujah. So it's going to be 0 minus 4 squared over 2 plus 4 times 4 minus, when I plug in a 3, I'm going to get minus 2/3 times a 1, right? When I plug in a 3 right here, that's times a 1. Minus 9 halves minus 4 times 3. Okay, let's do a little bit of cheating here. 4 squared divided by 2 is minus 8 there. Plus a 16. Oh, we need a common denominator here. 6, right? So that's going to be a minus 4, minus 27, minus 36. Because that's 12, right? That's minus 36 over 6. All those negatives? Oh, no. No. No, no. This is a positive right here. Right? Plus 4. Yeah. That's a plus right there. So this is going to equal, in this bracket, I have a positive 8. This bracket's what? Minus 4 minus 27 is minus 31. I don't like this at all. I don't like this at all. Because it's not coming out to 1/6. We have a 1z 2z error somewhere. So 4 times 3 is 12. That's 36. Oh, wait a minute. Wait a minute. 4 times 3 is 12. times 6 should be a 72. I agree. Okay, this should be better. So 31 minus 72 is 41. That's got the wrong sign. It's going to be a plus minus 40. So 31 minus 31 plus 72 is a positive 41 over 6. And we're not quite there. Because this is 48 over 6 minus 41 over 6. And that is 7/6. So I'm off by a 1 there. So well, I'll let you go. I'll find that. I'll find the onesie twosie, but you get the point. That we can swap the order of the integration. That's the point of this third way. Okay, so we're gonna do Friday. Tomorrow's gonna be chapter 4. King.
So we can go back to chapter 4.
Chapter 4. Chapter 4 was the Riemann integral.
Oh.
YouTube had me for chapter 4. And it was good once we were done, but that big summation, you remember? Partitions of the interval? Yeah, Calc 1's about to go through that. They don't know, but they're going to do it at home after Thanksgiving.
Ooh.
That's going to be the online part.
Ooh, that's enough for me.
I know.
Thank you, Mr. Miller.
You're very welcome. Thank you guys. Stay healthy.